All right, so we get started. I'm gonna get into a little more of a deeper level of AI. I'm not gonna get into the actual specifics of how to calculate these models because again, they can be difficult, and even for me, I would have to sit down with a pencil and paper and actually mark my way through this stuff. But I'm gonna talk about it a little bit from a higher level standpoint. So we'll go over some simple matrix multiplication for an AI model. We're going to go into AI models, which is where we're going to get into some of the levels. I mentioned earlier BERT. We're going to get into different ones like that. And then end of this, we're going to talk about tools and some examples, such as the libraries that are used for an AGI. Okay. First, artificial neural networks and their multiplication. We'll get into that. As I mentioned before, so I kind of reused this slide so we can kind of get a start from where we were in the last one. I mentioned we're going to go through multiplying the rows by the vectors, and that will, this one specific column by this, or that row by this column will yield to this one specific number. You multiply it and add them together, and then you'll get that one value. And you're doing that throughout the entire neural network. For each node, we'll have probably a long vector of numbers. You multiply them through, and as you see here, each synapse is a line from one node to the next. So that one node at the top up there has 3 different synapses to it, which means it should have a vector of 3. Because it's taking an input from those 3 different neurons.
So each item in there is an attribute of a value that you capture from data repository or whatever.
Yes.
My vocabulary for this is very poor.
That's fine.
So how do you choose those 3 values going in to make the decision on that next node?
Okay, so initially, before you, I should get into the input layer first, and we'll probably talk about that next. Let me see if I have that in here. Actually, we can go into this part first. All right, so input layer is going to input some information, typically a number between 0 and 1. It should be normalized first because you can't compare things if it's in this wacky set of numbers or features. You can't use names or whatever. You have to convert it into some kind of encoding before you send it through the pipeline. So once you convert that through, it should be normalized, and that should be able to have some meaning for each one of these different nodes. And typically, what happens is there's 2 types. There's the input and there's the weight. The input is a value of any sort, typically 0 to 1, but it could be more than that in that scenario. And there's a weight. A weight vector is just determining from -1 to 1 what is the weight of this item compared to all the nodes around it. So, So for example, in our brains, right, we have one neuron that turns on based on maybe 1,000 different neurons connected to it. And based on all the other neurons connected to that one neuron, we determine if it's going to turn on or not. And that's based upon the weights or the activation from the other neurons that's telling me to turn this one on or not. So if I get into detail, this specific node here will only be activated if the weights from, well actually, we'll talk about activation later on, just for simplicity. Each one of these different synaptic connections are going into this one node, right? Each one has an input, right? And each one has a weight to it. And that weight is kept to that node, but the input changes. So we change the input each time to each iteration, but the weight is fixed to that specific node. And what happens is as you go through and pass data through each time, it adjusts the weights for that specific node. Did I answer your question? Yes, no, maybe?
Yeah, but how do you choose that second node? Was it A1 and A2 and A3?
Yes. They're called hidden layers, you can choose any size you want. What happens is the model would be able to determine discretely how to adjust the weights once you have defined it. So the more, I think who asked that question earlier? Was it you? Yeah. So the more nodes you have in there will help it determine more discretely for each one and figure out the weights associated to that node. So if you only have one node, it's useless because at that point everything's channeled through that one node. But if you have 1,000 or more, for example, discretely certain items can be defined through each node, like an image, a certain curve or an edge could be defined by certain nodes in this neuron. Did that answer your question? Okay, great. So back to the math part here. You have certain inputs. So features is x1, x2. Features, I mentioned before, is from the input can be like a piece of, for example, I have different combinations. I'm gonna pick up Pierre because Pierre's sitting right there. So I see, so a feature could be, I see eyes, I see a lips, and then through that network ends up being a person. Or a feature might be something else like a fish. You determine the different type of mammal it may be based upon the feature sets. So those are features that come in and they have their values. And then each one of those X's there are each input after the model has cycled through, 1,000, million, 100 million times. Right now I'm only showing 3 cycles. And this is supervised learning because we have a Y which has the output values. Typically in a unsupervised learning, you don't have the Y value because you don't know. But in supervised learning, you do. Okay. So getting a little more deeper into that, input time to weight, as I mentioned before, would be able to give me that particular value. And then over here, again, through the matrix multiplication, would take the one node multiplied by the weight, and same thing going forward for all the ones that are connected to that one node, as I showed here. That same multiplication we did here on the side here is pretty much that part down there. Sum them up, give me a new value. And that's going to be placed in for that particular matrix. All right. Now we get into the fun stuff. We're going to walk through this matrix multiplication system, and we're going to get into what you mentioned earlier about the sigmoid function down here, was to be able to calculate an activation function to move the node forward. So, input layer. Broken down, I'm only showing 4 sets of input here, all right? But again, there are 3 different input layer nodes. A bias is something we apply to all neural networks because we want to make sure that it never goes into this undefined situation. So we apply a bias set of 1 up top, which you can see over here is that one particular vector going down. And then we have those 2 over here are inputs, and it's just 0 and 1. It's very simple because we're using it for simplicity for this class here. So moving forward, we want to take, here's the feature sets. The first one's a feature set. We move forward from there. That is an input vector. That is the input vector for the bias. So you can see here that there is the input and there are the weights associated. The weights are those red lines connecting to all 3 of those yellow nodes. You see what I'm saying? So you see there's 2 parts here. There's the actual input vector, which is typically only 1 for 1 entry. Good.
So the weight's at 0.5, is that because you want to give it an unbiased, you have an even chance of going one way or another, and then as the machine learns and it provides a loss function or something, it adjusts those weights to be correct over time? So
initially when you first start, you are giving an arbitrary set of values, and 0.5 is a good setting point. Or 0, well, I wouldn't use 0 because sometimes they become problems, but a lot of times they do use zeros to start off with, but we use 0.5 in this scenario. But yeah, those are the weights you start with, and as you're talking about, those weight vectors is what stays. The input goes away. No one cares about the input. Once you use the input one time and move on to the next value, the input's lost. It's not necessary anymore. What's kept are the weight vectors. That one matrix over there in the middle is kept because those are kind of the signature or the pattern that represents a particular action moving forward. So keep the weights, forget the input. The input are good data to bring it through, to train. You train your data through the input, but the weights are kept as a model moving forward, and you put that into production and use that to determine if there's a cat or dog or whatever you want to figure out. So here's one feature set. outside the bias. Again, same concept. You have the weights, you have the input layer, and you have the connections to those input layers. All right, so when we do one calculation, we mentioned earlier that matrix multiplication, you take the row by the value. For that one input node 1, what here, well, I kind of messed this up a little bit, but this is supposed to be for the one bias value input here. If you do another one for input node 2, second column, or second row by second column, give me that point value there. You multiply it through, and you add them up, and that's the value for that second node. So if I want to do all of them for that one node in the middle, 2 there, I have to apply that second row here by the entire matrix to give me this one node of values. You see that there. Then for the entire layer, I have, for all of them, you multiply everything through and get the second layer, the hidden layer state. And then we would apply, now this had sigmoid function, I switched it to ReLU because ReLU is the current version we're using now. People have forgotten about the sigmoid function because it has a lot of dropout issues and issues with exploding gradients that goes over and beyond, or it goes towards 0 after a long iterations of data. So he said, let's get rid of that and just go ahead and use something called ReLU, which is a function that's either 0 or above, and keeps going on for that value. So same thing happens again for the next layer. So you can see this happens for each layer moving forward. Now that I have this new set of, now again, the weights are, again, the next layer of weights. We have the first layer of weights up here, and the next layer of weights here, and we have output. Output should be kind of defined, but we'll talk about that in a moment. All right, so we, again, multiply the new weights, get the output layer, and then apply another ReLU function, and we check with our output. And move forward. Oh. That's it for that piece of multiplication. Any questions?
So the weights you mentioned, those are the weights for the equation y is equal to mx plus b.
Yes.
Identify the weight m and the b part.
B is the bias.
The bias, right?
Yes.
So that's the equation for a straight line.
Yes.
Each neuron is trying to create a straight line. That's what I understand.
Yes. In some sense, it's the simplest way when dealing with a matrix multiplication. It's a simple way of creating a linear from one node to the next. It is. Okay.
Each neuron is trying to create a straight line.
In some degree, yes.
Yeah, but where does the activation function come? Like, where does
Oh.
that curve fit?
So the activation function comes in right after you have computed that value you just mentioned. Then we apply that value and squish it in here. The value you just calculated, the wx plus b, the mx plus b. We squish it in here and push that value in between 0 and 1, or negative 1 and 1. But we don't use this function anymore. We kind of keep the current value and move that forward.
Yeah, we use that for what? We use the output of this activation function. We use where?
Into the next neuron. So
As a weight.
as the weight into the next neuron. So when we calculate the adjusted weight, we will keep the weight there, and that will be the actual input into the next neuron. Because the thing about it is, this value is considered the actual neuron input. You see what I'm saying? And then we use that input into the next one, and then of course there's a long layer of whatever size that is, and compute that. Any more questions?